Hey everyone, now we're going to do graphical analysis which expresses the uncertainty in the relationship consistent with the uncertainty in the data. Basically put a full expression of uncertainties onto our graph. So here's some data I've produced earlier. We're looking at the relationship between the distance a ball rolls down a slope and the time it takes to traverse that distance. Both these variables have uncertainties. We've got the uncertainty in d, but we've already transformed our variable because we know the relationship is with the square root of d. So we've transformed our uncertainty in d into the uncertainty in the square root of d. If you don't understand how to do that, see another video. So we've got all our data. Let's take it all and let's put it into Plotly, which you see I have already done. And so I've got my graph of t against the square root of d. I've got my line of best fit in here, and the only thing left for me to do is to extend that line backwards a bit. So we'll put that at negative 0.05 and up to 1. So I get my line going across the origin. Right. So the first thing we need to do is to add our error bars. So we go to the traces section. We scroll down until we find the error bars. There they are. X and Y. Let's use symmetric. Means it's the same each side. Defaults to 10%. We can't use that, so we need to select our data. We have calculated our uncertainty in the square root of d. And they're tiny. Look at that. And then for our Y error bars, we go for symmetric as well. That also defaults to 10%. And we want to use the data where we've calculated the uncertainty. Oh, scroll down a bit more. The uncertainty in t. And there's our error bars on there. And we can see most of the uncertainty is because of t, not because of our measurement of d, because they're really tiny and the vertical ones are really big in comparison. Let's go back to our curve fitting. Now let's put on our error line. We add another fit. And let's put it on, trace 0. Run it. You can see it's only gone through the range of the data and we want to extend it back, so let's go advanced, scroll down for our minimum, negative 0.05 up to 1, and run that, and they're lying on top of each other. So first thing we want to do is change the color and the labels. So let's go back to our traces again, and you'll see there's trace 0, and we scroll down till we see the fit of trace 0. That's the first one we did. Let's change that to the line of best fit, and you'll see the top one's changed already. Let's go down and do the same thing for the line of the second one, and let's call that the line of worst fit. Okay, and let's make the line of worst fit red or something. Doesn't matter which one you use, but there you go. That one's red. Okay, very good. So now we've got two different lines. Go back to our curve fitting, and we've got our two traces. Unfortunately, these labels don't change, but it's the second one. Right, first thing we need to do is we need to lock our gradient. And this is 1.3, so let's try 1.4. You can see it's a bit steeper, but still well inside those error bars. Let's try 1.5. It's even a bit steeper. And you can see that it's starting to, down here, it's just about to leave this point down here, the little box defined by the error bars. So what I'm going to do is I'm going to lock my Y into now as well, and increase my gradient a little bit more. 1.6. Oh, now it's gone too high. It's gone off the top out there, you can see, and this is a little bit in, so I could make this a bit smaller. So negative, let's make that negative 0.14. Let's try that. Bring it down a bit. Bring my gradient up a bit. 1.65. Run that. Oh, too much. Let's try this down. 1.15. And you just keep on mucking around until you are happy with where it goes. That's too high. 1.61. Run that. Still a bit high. I think maybe 1.60 was right. Now I think this line of worst fit is the most extreme value that we can fit onto those in between the error lines. At the bottom, it fits just inside the rectangle formed by the error bars, and at the top, it's also in the rectangle formed by the error bars. And it's staying inside all the rest of the error bars. This, I think, is our most extreme line of worst fit. So having fitted the line of worst fit to the error bars, we now need to copy across our graph. But the first thing we want to do is make sure both of the intercept datas are shown. So we scroll down, and we've now got the parameter estimates for the line of best fit showing and for the line of worst fit showing. So let's copy that into our Google Doc. There we go. And we now need to record our parameters. So for our line of best fit, let's use the equations. So our gradient is equal to 1.327 22 is what it's shown, and our y-intercept, oh yes, keep on using the equations, c is equal to negative 0.0091. Now our line of worst fit, and let's use the equation again. Now we're going to use that little index form because our symbolism is m star for the line of worst fit, equals, now this one is 1.6. Now the moment we've gone to those 1 decimal place accuracy, so we need to round this to 1 decimal place because there's no point otherwise, so it's equal to 1.3. And if we go down for our y-intercept, similarly we've got c star equals negative 0.15, and again, given we've got 2 decimal place accuracy there, we need to take this to 2 decimal place, which is negative 0.01. So we now calculate our uncertainty in our gradient. So this is delta m, which is equal to the, now it's officially the absolute value, which is those symbols. So we've got our m star, take away our m value, and I've put them the right way around here, so it's going to be equaling to the absolute value of 1.6 take away 1.3, which is very clearly 0.3, and we might as well save ourselves some time and do the C value as well, and just change those two C's. C. Oh, what happened there? Yeah. Difference between the C values, and that equals, I might as well copy that too, save me some time. And this is going to be negative 0.15, take away negative 0.01, which is really clearly 0.14. So there's the uncertainty in our gradient and the uncertainty in our y-intercept.